Good morning, Year 12. So we are moving on to some Year 13 topics now, and we're going to start with Trigonometry 2. So we're going to look at the other way of measuring angles. So you are aware we've always measured angles in degrees, and we'll talk about why we've done that in a minute. But you're also aware that there are other ways of measuring angles because we've talked about radians. And you'll know on your calculator there's another mode for angles, or there's another two modes for angles, and one of those is radians. So that's what we're going to introduce today. But let's just think about degrees and why we measure in degrees at the moment. The 360 degrees is very much an arbitrary value that the ancient Babylonians came up with. Okay, so it's just as a reminder, an angle is a measure of rotation, how far we're rotating. And 1 degree is 1/360th of a full turn. And as I've said, that's down to the ancient Babylonians. So where did they get 360 from? So it's thought that it used to be the approximate number of days in a year. So we know now that there's 365¼ days in a year, but at that time it was thought there were 360. So that's where the number came from. So it's got nothing to do with the circle itself. It is just an arbitrary value. But the nice thing about 360 is that it has a lot of factors. Okay, so it's easy to talk about fractions of the circle because you can divide 360 into lots of different fractions. So, for example, 4/9 is equal to 160, and we know a half is 180, a quarter is 90, and so on. Okay, so that's where the 360 came from. So it's actually more useful, however, to measure angles in radians, because radians has got something to do with the circle. So we're going to look at what the definition of a radian is first. Okay, and you will find in mathematical and scientific applications, and when we get to calculus, differentiating and integrating, it's more appropriate to measure angles in radians. Okay, so what's the definition? Okay, so look at this circle here. We've got a sector. So remember from your GCSE, a sector is like a slice of the circle, slice of pie from the circle. Okay, and we've got these two radiuses here, and then you've got the arc. So that's the section of the circumference. Okay, that goes from this radius to this radius. Now, if that arc is the length of a radius, okay, we say the angle at the centre, okay, of that sector is 1 radian. Okay, so it's written here, 1 radian is defined as the angle subtended at the centre of a circle by an arc whose length is equal to the radius of the circle. Okay, so here's your sector, radius, radius, and the arc is also 1 radius long, and then you've got this radian. So radian is much bigger than a degree, okay, but there is a connection to the circle. Okay, oops, put that back. Okay, so we would write 1 radian either as 1 rad or 1 with this little c instead of a degree. You've got a little c there. Okay, so how then do we convert between radians and degrees? Well, it's useful then to think about the whole circle. Okay, so we know the circumference of a circle is 2 pi r. We learnt that at GCSE. Okay, so if I know there are 2 pi lots of radiuses around the edge of the circle, 1 full turn in radians is 2 pi radians. So let me just go through that again. Okay, so we know that 1 radian is 1 radius here. We know all the way around the circle is 2 pi lots of these radiuses. Okay, so there must be 2 pi lots of radians. So a full turn is 2 pi radians. So that means we normally think about a full turn as 360 degrees. So 360 degrees is equivalent to 2 pi radians. Okay, let's put in rad there. Okay. Okay, pi radians is equal to 180 degrees. So you do need to learn this, okay? This is what we're going to be relying on from now. I guess the most important one is that pi radians is equal to 180 degrees. If you can remember that one, everything else can be calculated from there, okay? So let me just get rid of that and we'll look at the next bit. So what are the other equivalents? Okay, so it says find some other equivalents. What is 1 rad in degrees and what is 1 degree in rads? So we know that pi radians is 180 degrees. So I've set up my little table to help me here. Okay, so I know that pi rads is 180 degrees. Okay, I want to work out what 1 rad is. So let me put the 1 into the rad column. Okay, radians column. Okay, how do I get from pi to 1? Well, I would divide by pi. Okay, so if I've divided by pi on that side, I've got to divide by pi on that side. Okay, so this is going to be 180 over pi. So 1 rad is 180 degrees divided by pi. So if I wanted to work out any other number of radians in degrees, I would do 180 divided by pi times the number of radians I had. What about the other way around? What is 1 degree in rads? Okay, so let me just clear my table. So this time I want to work out what 1 degree, okay, and how many rads that will be. So this time, how do I get from 180 to 1? I divide by 180. Okay, if I've done that on this side, I need to do the same on this side. So in that column, I have pi divided by 180. Okay, so 1 degree is pi over 180. Okay, now as with a lot of things at GCSE, when we were working things out to do with circles, if we didn't have a calculator, we often left our answers in terms of pi. Where you can, with radians, you tend to leave your answers in terms of pi. It's not always possible, okay? But for example, if I was looking for 90 degrees, okay, if I know pi is 180 degrees, I'd know that 90 degrees was half pi or pi by 2. So I would leave it as pi by 2, and I know that pi by 2 is 90 degrees, okay? Same with 30 degrees. I know that 30 degrees is a sixth of 180, so that would be pi by 6, and I'd leave it as pi by 6. So there are certain ones that you're going to need to learn, okay, or be able to work out, and others that we can't leave in terms of pi, you just use the decimal, okay? So let's just have a quick look at summarising this into a little diagram. Okay, so if we're converting from radians and degrees, if we start with degrees, we divide by 180 and multiply by pi, and that will give us radians. If we started with radians, we divide by pi and multiply by 180. So let's do a quick example. Let's do 60 degrees, and I want to turn that into radians. So this says divide by 180 multiplied by pi. So if I divide that by 180 and multiply by pi, okay? Now, where possible, I want to cancel this fraction. So I can see, obviously, you can divide both by 10, and then I can divide 6 and 18 are both divisible by 6. So go 1 and 3, so it's a third. So the answer to 60 degrees, okay, 60 degrees is a third pi, or pi by 3, okay? Okay, so let's have a look at 225. So again, we're going to divide by 180 and multiply by pi. Okay, so you can just pop that straight into your calculator to help you cancel it, put it in the fraction part. Okay, and then you should get 5/4 pi. Okay, so 225 degrees is the same as 5/4 pi radians. Okay, if we were going to go the other way, okay, so if I gave you 2/3 pi radians and I wanted that in degrees, okay, so for this one you would divide by pi and multiply by 180. So I'm going to divide by pi and multiply 180. So you can see if your radians is in terms of pi, that's quite nice because the pi's just cancel out. Okay, and then you're just doing 2/3 of 180. Well, we know that 1/3 of 180 is 60, so 2/3 of 180 is going to be 120 degrees. Okay, all right. You might, if it's not in terms of pi, that's fine. So let's say we had 0.5 radians. Okay, so I would just divide that by pi and times 180, and then I just put that in my calculator to get a decimal answer. Okay, so we just pop the calculator up here. Okay, you do 0.5 divided by shift pi and then multiply by 180. Okay, you get 28.6 degrees. Okay, so that's to one decimal place, obviously. Okay. Okay, so we've converted from radians to degrees and degrees to radians. So if you have a look at page 259 in your textbook, there should be an exercise 1.1, and that's all that is doing, is practicing converting radians to degrees and degrees to radians. Okay, so you might want to stop at this point and get that exercise done before you use on. Don't forget you can use your calculator for this. It's not a non-calculator exercise. So in terms of cancelling fractions, use your calculator. Okay, if you just want to type that in, they're not with the ClassWiz calculators, it will give it to you in terms of pi anyway, so that's fine. So it shouldn't take you too long to do that exercise. So when you're ready, press play and we'll look at some of the measurements that we studied at GCSE and how the formulas changed for radians. So at GCSE we used to look at measuring the arc length, and if you remember, the formula we used was we took the angle and we divided it by 360. Okay, so that worked out the fraction, okay, of the circle that we were looking at, and then we multiplied by 2 pi r. Okay, and that gave us the length of the arc. So quite a complicated formula. So let's have a look at radians. Okay, so we've already defined that 1 radian here is when the arc length is r. Okay, that's the definition we've given to that angle. 1 radian is when this arc length is r. So if the angle at the centre is 1 radian, then the length of the arc is r. That's what we said it was going to be, so that's true. So if we then just doubled the angle, so we made it 2 radians, then the arc length would double and become 2r. Okay, if the angle at the centre was 0.3 radians, okay, so we were making it just 0.3 of the angle at the centre, then the arc length would also be 0.3 of the original arc length, so it would be 0.3r. So in general, the arc length is just the angle in radians multiplied by the radius. So look at the difference in the formulas. That's your formula from GCSE. This is your formula when we're working in radians. So it is just the angle, but it has to be in radians, multiplied by r, the radius. Okay? Okay, so let's have a look then at the other measurement, which was to work out the area of the sector. Okay, so again, remember that this 1 radian here means that this length here is r, okay? And the angle at the centre of a full circle is always 2 pi radians. So if I go all the way around, that's 2 pi radians. So the formula we had from GCSE to find the area was, again, we found the fraction by doing the angle in degrees, okay, divided by 360. Let me write that one up here. It was the angle in degrees divided by 360, because that worked out the fraction of the circle we were talking about, and then you multiplied by pi r squared, which was the area of the whole circle. Okay, so we've already said now that 360 degrees is actually 2 pi radians. So if we change this from degrees to radians, it would be the angle in radians divided by 2 pi times pi r squared. But you can see now I'm dividing by a pi, I'm multiplying by a pi. So if I cancel those out, I get the angle divided by 2, or half the angle, times r squared. Okay, and this is the formula that you need to know, half r squared theta, where the angle is measured in radians. Okay, and there it is again from degrees. But again, a much simpler formula than we had here. You will need to know that formula. You won't be given it. You need to learn it. Same with the length of an arc. Okay. Okay, let's have a look at a few examples. So the first one, giving your answer in terms of pi, find the arc length and the sector area of a circle of radius 6 centimetres with an angle of 3/4 pi radians at the centre. So let's start with the arc. So arc length, if you remember, is just theta r, where theta is measured in radians. Okay, so we know that the angle is 3/4 pi, so let's just substitute that in there. And we know, okay, that the radius is 6 centimetres, so that's times 6. Okay, so I'm just going to do 3/4 times 6 and leave the answer in terms of pi. So let's just get the calculator up. So we've got, here we go, 3/4 times 6, okay, which is 4.5 or 9/2. Okay, so it's just 4.5 pi. Okay, so that one's nice and straightforward. Then the area, okay, of the sector is a half theta r squared. It's only the r that's squared, remember, not the theta. Okay, so again, we know that theta is 3/4 pi, so there's a half times 3/4 pi, okay, multiplied by 6 squared. Okay, so I can do this bit, that's going to be 3/8. So on my calculator, I'm going to do 3/8 times 36. You could type the whole thing in if you want. It's up to you. Okay, so I'm just going to type in 3/8, so fraction, got 3/8 multiplied by 36 is going to be 27/2, which is 13.5. So the answer is 13.5. And I missed the units on the first one, so it's 13.5 pi. Now the measurement was in centimetres, this is an area, so it's centimetres squared, and the top one should have been centimetres because it's a length, so don't forget your units. Okay, so that's just a fairly straightforward find the area, find the arc length. So here we've got a bit of a problem. It says a wheel of radius 2 metres rolls 0.5 metres along the ground. How many radians has it turned? So if we just do a quick sketch of a circle. Okay, so here's my wheel. Okay, okay, it's got a centre now. So we know the radius, is 2 metres. So let me draw that in. So there's my radius, and that's 2. Okay, and If it rolls along the ground 0.5 metres, okay, that means 0.5 metres of the wheel has touched the surface of the ground. So we're talking about the arc length here being 0.5 metres, okay? So I just need another radius there just to finish that sector off there. Okay, so I've got 2 metres and this is 0.5. So if remember, okay, so we know the arc length is 0.5. We don't know theta, but we know the radius is 2. Okay, so we've got 0.5 equals theta times 2. So obviously to find theta, I need to divide both sides by 2. So I'm going to do 0.5 over 2 equals theta. Okay, and half of 0.5 we should know is a quarter, or 0.25. So theta is 0.25. That's not 0.25 pi, it is just 0.25. Okay, there were no pi's involved in this one. Okay, so 0.25, and I'll use the little c for radians, or you could type in rad. Okay, so that's that one. The last problem one here, okay, we've got 2 circles. We've got a shaded part of a circle here, which is made up from a large sector, take away a smaller sector. Okay, we're asked to find the perimeter of that shaded section, and we're asked to find the area of the shaded section. We're also told that the angle is pi by 3. So we'll start with perimeter. So for the perimeter, we need to know this bit here, the large arc, okay, and we need to know this small arc. And then we're told that this length here is 2, and so this also must be 2 here. Okay, so let's start with the large arc. So if you remember, arc is theta r, okay, and theta we're told is 1/3 pi. Okay, so that's 1/3 pi times the radius. So for the large arc, the radius is 4, okay, because it's from the centre all the way out. So we've got 1/3 pi times 4, which is 4/3 pi centimetres. So I'm leaving that still in pi, and I'm going to convert it to a decimal right at the end of the question. Okay, small arc, similar, is theta r, but this time the radius is 2, so we get that it's 1/3 pi times 2, which is 2/3 pi centimetres. So to find out the perimeter, I'm going to do the large arc plus the small arc plus 2 plus 2. So that's what we've got here. So we've got 4/3 pi plus 2/3 pi plus 2 plus 2. Well, if I add those together, I get 6/3 pi plus 4. 6/3 pi is 2 pi. So we've got 2 pi plus 4. So if I just pop that in the calculator now. Okay, so we've got 2 times pi plus 4 is 10.28 centimetres. So I know now, if I take a photo of that and just paste it, there we go, it's 10.2831, and that's centimetres, and you'd obviously round that to 1 or 2 decimal places. Okay, so that's perimeter. Okay, so area, okay, in red. Okay, so if we just pop up to the question again, we would need to find the area of the large sector, and we would subtract the area of the small sector. So if you remember, the area is 1/2 times theta times r squared. Okay, theta is still pi by 3, so that's 1/2 pi by 3. Now for the large one, the radius was 4, so that's going to be 4 squared. Okay, so that's going to be, this becomes pi by 6 times 16. So that's the large one. I'm going to leave it like that for now and then pop it in the calculator. And then for the small one, okay, it's going to be same formula. So 1/2 theta times r squared. So that's going to be 1/2 times pi by 3. But this time the radius is 2, so it's going to be times 2 squared. Okay, Okay, and so that's going to be pi by 6. I'm going to jump a bit, sorry. That's going to be pi by 6. I've missed the 2 there. Okay, times 4. Okay, so I've got pi by 6 times 16, pi by 6 times 4, and remember we've got to subtract. If we come back here, I've got to find the large sector, subtract the small sector. Oops. So we're going to do 16 pi by 6, subtract 4 pi by 6. Okay, and at this point I can see the denominators are the same. 16 pi take away 14 pi is 12 pi, so it's 12 pi by 6. Okay, and again I can see 12 divided by 6 is 2, so it's just 2 pi. Okay, so I'll pop 2 pi in my calculator. 2 times pi is 2 pi. 6.28. Okay, so again, let me just take a photo of that and paste it. Okay, and that is in centimetres squared this time. Okay. Okay, so there's the area again, round that accordingly. All right. Okay, so there's a few examples for you to have a go at there. So I would now turn to page 259 to 261. You should have already done exercise 1.1. Have a look at exercise 1.2. And if you get that done as soon as possible, that'd be brilliant. Okay, let me know how you're getting on.